Hello, my name is Kamburjan from the University of Oslo, and I'm going to talk about deductive verification of hybrid objects. So first, what's deductive verification? It's a technique for example, safety proofs, which is based on logical reasoning, which means that we apply deduction based on logical rules to conclude that the system is safe in some sense, provided that we have a specification for it. This kind of verification has been done for quite big programming languages, for example for Java in the Key project or the Key tool, for a big subset of C in Frama C, and for C# with the Daphne tool. And there are several advantages to deductive verification. One of it is that you don't suffer from state space explosion. Because you use reasoning to conclude that something is safe, you don't care about finiteness or finding a fixed point or even how big your space is, as long as you have some rules to operate on it. The downside is that it requires quite fine-grained specification, right? So I can't just say I don't want to reach this kind of states and push a button. Instead, I have to specify more invariants, for example, more contracts. The good thing is that what we have learned from these complex languages is that we can apply the same modularization techniques that we have for the language itself, like methods, also for specification and verification. So in an object-oriented language, if we have objects, we have object invariants for specification, and then proof obligations based on object invariants. Similarly, if we have methods, we have method contracts, and then we have proof obligations if we look at each method in isolation. So here's one example of how this is done in an object-oriented setting. We have some object, it has some methods, and you want to prove that object has the invariant I. So how do we do this? For example, in dynamic logic, what we can do is having this formula which says, I assume that the invariant holds, then I execute the body of my method, which is the statement S, and then I have to prove that the invariant still holds afterwards. And this is simplified, of course, how a proof obligations for discrete system works. Well, why can we do this? Because in a discrete setting, my state can only change if I execute a method. Right? So let's say I have a variable, so in time advances, the state does not change. Right? Some method has to be executed to change it, and then it stays constant again until the next method runs. So if I check the invariant at the end of each method, right, of all possible executions, under the assumption that it always holds, then this shows that the invariant always holds, right? Because after the end of this one and the beginning of this method execution, nothing can happen. This is obviously not the case for hybrid systems, because now, after this method runs, and before the next method starts, the state actually changes. And let's say we have the invariant that the state stays above this line. You will not know this if you only look at the post state, at the post condition of this method execution, that here you did below this line, because there is no method active around here. So how do we apply these principles to hybrid systems? Right? How do we apply the ideas that were developed for complex object-oriented systems in a discrete setting to hybrid systems? So first of all, we need an object-oriented language for hybrid systems. We are going to use hybrid active objects, which is an extension of active objects to hybrid systems. So first, active objects without hybrid systems. So they are an extension of objects for distributed systems where each object has its own node. These nodes and objects are strongly encapsulated, meaning that one object cannot access the fields of another object, even if they are in the same class. The objects can only communicate using the active concurrency model, meaning they can only send each other asynchronous method calls, and if they need to retrieve the result of this method call, they can access futures to synchronize on them. But without that, they can use only asynchronous method calls. Also similarly, characters, for each object at each point in time, there's only one thread active, and this thread cannot be descheduled against its own will, meaning it has to terminate before another process can be started or can be rescheduled. One way to do this is to terminate. Another way is called condition synchronization, which means that we have a special statement which says, I suspend myself, but the process can be rescheduled once a certain Boolean condition holds. Also, we have special statements to deal with time. So there is a global time, which is always the same for all objects, and we have a special orchestrator which advances time once there is nothing more to be done in this time step, and somebody has required that the state advances. So active objects have been implemented in several languages and are part of libraries for Java, for example. The, let's say, most prominent example is ABS. And just as the examples that I will show you later, it follows the programming as modeling paradigm, which means that we have programs, but they are not the implementation of the system, they are still an abstraction of it. So we are dealing with models of hybrid systems. There have been several case studies with ABS. For example, industrial cloud systems have been modeled and analyzed, railway operations have been modeled and also verified using the very same ideas that I have presented to you a moment ago. And there have been other applications, for example, memory models. So it's a good host language if you want to deal with deductive verification, because we can assume that the non-hybrid part has been mostly been taken care of. But indeed, we will use some of the ideas that have been developed for ABS. So here's an example. We have a class car. It has several fields. For example, it has a tick, how often it checks its sensor. It has a sensor, it has a pointer to the next car in front of it, and it has some other fields, for example a minimum and a maximum distance to the next car. So here we have a method. What the method is doing is, while I'm in platooning mode, so which is a Boolean field here, I wait until I have a car in front of me, then I ask the sensor that I have, what's the distance to the next car? I retrieve the result once the sensor has computed it, and then I react on the distance accordingly. And I also advance time by tick time units before I repeat the loop. The important part here is that between the two awaits, nobody else can access my state. So I know that the next car is a certain car here, and it will be the same car here. Because another object can never access this field, and without awaits, no other thread can run on the same object. So we can in some sense pretend from here to here that we are in a sequential setting. To have hybrid extension, we need to do two things. First, we need to somehow describe what the behavior is, and we describe the behavior on object level. So each class has a special physical block, which describes physical variables, which are described by the initial value at creation and an ODE. So we have always the same number of ODEs as physical variables, and we can refer to other fields in our initial conditions. So this here says I have a variable x1, I have a variable x2, I have a variable x3. x3 starts at 5 and then follows this ODE, and x2 follows this ODE, and x1 follows this one. Then we need a way to react to physical fields, and we add a special kind of condition synchronization. So we have a special await, which has this diff here, and this expresses that this method can be scheduled once x1 is bigger than x2, and x1 is also bigger than x3. And then it continues as before. And for this kind of await statements, we only allow physical fields, and we only allow weak inequalities. Semantics of this is an urgent semantics, which means that I will schedule it as soon as possible this condition holds. So we need weak inequalities to have event boundaries. Note that the continuous behavior here is described for each object in this physical block, and inside the methods I cannot refer to it explicitly, only to the variables within, which means that I do not have to take care of where exactly I have to interleave continuous behavior and discrete behavior, because this is taken care of me by the scheduler, which deals with the awaits, and when time advances, it advances the state accordingly to these equations. So here's an example. we have a water tank, so we have something that can hold water. We have a sensor for level and the flow, and we can let water in and we can let water out. So we have two physical variables, one for the water level, one for the water flow, where the water flow is actually constant. Then we have an initial block, which calls two methods, up and low, where up makes sure that the tank does not overflow, and low makes sure that the tank is never empty, and by empty we mean that it never falls below 3. So how do these methods look like? For example, low waits until the level falls below 3 and water is still leaking, then it adds water to the tank and calls itself, and up does the same thing except that it waits until the level is above 10. Now that if we start between 3 and 10 and we have an urgent semantics, then this means that it will trigger at exactly 3 and this one will trigger at exactly 10. So if you simulate this, and there is a simulator for this language, and you start with 5, you would see the behavior that you would expect, which means that you fall to 3, then low triggers, then you go to 10, then up triggers, and so on. But now we want to prove that this is indeed an invariant of the system if I start with a safe state. So for all possible input values. How do we do this? Well, as a reminder, we want to have something like this for every method, but now we have the problem that we somehow need to refer to ODEs in our statement and maybe in the post condition. But luckily for us, there is already a logic which can do that, and that's the differential dynamic logic, which is implemented in the Chimera tool. And it's a standard first order logic over the reals, so it has quantifiers, usual connectives, has a modality, but inside the modality there are algebraic hybrid programs, which is a very, very simple while language. So it has tests, so I can test whether a certain formula holds, and if the formula does not hold, I discard the run. I have assignment, I have non-deterministic assignment where I pick a random value and assign it to V. But most importantly, I have this statement which says, follow this ODE as long as you stay in the region defined by phi, where phi is another formula. Right? It is important to note that this statement here is non-deterministic. So it does not tell you how long to follow the ODE. Yeah, you basically pick non-deterministically how long you will follow it. And every time is okay as long as you stay inside of phi. Here's an example. I have a clock which is called x. I set it to 0 in the beginning. Then I follow this ODE where I say it has slope 1 and x is less or equal to 5. So once this terminates at this point, x is something between 0 and 5, but I can, as always, use the guards to model event boundaries. So I say, okay, x must be bigger or equal than 5, and afterwards I can check that I describe exactly the event boundary that x over 5. So if I feed this formula into Chimera x, it will tell me that this formula is indeed valid. Now that we have a logic and we have a language, let's look at how we can combine them for verification. First, a few smaller assumptions that we need. We assume that every method starts with an await diff statement, and if it does not, we just add an await diff true, which does not change the semantics. And we denote the guard of this starting await with trigger of m. We assume that only real variables are manipulated, which is needed because you want to translate it into differential dynamic logic, and it does not have data types, it only has real variables. And just a notation, weak negation is denoted with this tilde over the negation, and it acts exactly the same as a normal negation, except that if you negate a weak inequality, it preserves the event boundary. So the first thing is, what does it mean that an object is safe or has the invariant? In discrete objects, we only say that an object is safe if phi holds whenever a method starts. Now we're at the second condition. It has also to hold whenever time advances. And for presentation's sake, the next few minutes we're going to assume that there are no other waits, no gets, and no duration. But of course, the paper describes all the details. In the later parts of this presentation, I will talk a little bit more about how we handle this kind of things. So let's jump directly into it. Let's say we have a class, it has dynamics, it has a precondition in the sense of a precondition for the constructor, and it has an invariant. We need to prove for each method the following. If the invariant holds and the method is triggered, then we execute the body of the method where, because we only manipulate real variables and all these special primitives are missing, this is almost a one-to-one mapping. And as the post condition, we prove that the invariant holds now and that the invariant will hold when I follow the ODE forever. Which means that, let's assume we are looking at the method which is responsible for this jump here. We prove that here the invariant holds and it would hold forever. So if it dips below here, we will detect this and say it's not safe, and if it does not, we will say it is safe. We will completely ignore at this point that there are other methods. We just say, what if no other method is called? What if no other method is active, right? So at the most basic case, we just look at each method and say it has to establish that the dynamics are safe forever. We do the same thing for the constructor, except instead of assuming the invariant, which we obviously cannot do, we assume that the precondition holds. So this is called the basic region, because the basic region where the dynamics have to be safe is just everything. And what we can do with it is we get a very nice modularity results if I add a method to a class or if I remove a method for a class. I do have to re-verify at least one method. So if I remove a method, then the class is still safe, because it doesn't affect the safety of other methods. And if I add a new method, I only have to verify this new method. I do not have to touch the old proof applications. So we are very modular, but of course we are very imprecise, because most of the time we have some kind of control cycle, which actually makes sure that we do not run forever. We do not have to establish safety forever. So if I have a self-stabilizing cycle without an internal control cycle, this holds. But for example, we cannot even verify our water tank. But basic regions are a baseline that we have, because we can apply them without using any additional information. So now let's say I want to check how long I have to make sure that the dynamics are true. So I have to make sure that at some point some other method takes over before it becomes unsafe. Well, what can I do? What I can do is, and this is called locally controlled regions, can look at the set of methods which are guaranteed to be called in every execution of a method. So we denote the set CM, and then my proof application looks as follows. Assume the invariant, this modality looks as before. I still have to prove that the invariant holds in the post condition, but now I have only to show that the ODE, so the dynamics, are only safe while I'm not triggering any of these methods. Because if the trigger holds, then another method will take over. I have guaranteed that the object invariant starts when it takes over. I do not have to guarantee that it holds afterwards. This is the task of the next method. So note here's the weak negation, so we have an event boundary. So again, let's look at this method here. And let's say I call a method where the trigger is everything outside the gray region. Right? So let's say I have an ellipse here, and I trigger when I leave it. So this may be unsafe, right? So here there's an intersection of the post region with the non-safe region. So now I check if I follow the dynamics inside this post region. Am I safe or not? Because at the latest here at the boundary, another method will take over. And here I can show, okay, this method will be safe. I will detect that this method is not safe, because here the dynamics in whatever post region will dip below. It does not have to be the case that these overlap. So, for example, if the trigger is that this variable falls below this line, then obviously it's safe until the next method holds, because, well, I can only advance inside this region, and this region is trivially safe. I still need to verify every method, because I need to make sure that I do not make a jump in the discrete part which goes into the unsafe region. we have here the invariant in two places, in the post condition and then in the post region. The reason for this is that I may trigger a method directly afterwards. Right? So I do not advance time, I go directly into the next method. And in this case, this whole thing here, so this one will become false, and then this part of the post condition will become true. So I need to establish that the invariant holds even if I do not execute the dynamics. So for basic regions, this actually can be simplified, but here I cannot simplify it anymore because I can have the situation where this one is actually empty. Great. So now let's look at what we have done in more detail. Well, modularity suffers because if I now change the trigger of a method, I need to re-verify A, the method, and B, every method who calls it, because they are safe for a certain post region. And if I change the post region, I need to re-verify it. But I can now verify not the water tank as I demonstrated it, but the variant of it. So here's an example. I still have my water tank. The level starts at 5 now, so we don't have to care about the constructor, and I only call low, which means that I only look whether the water is empty or not, because I know that the flow is negative in the beginning. And then the low method is modified. It waits until the level falls below 3, sets the low flow to a positive value, and then calls up. So this is 0. I would need to change something here, but anyway. So now what's the proof obligation for low? I assumed invariant. I assume that the level is below 3 because I'm triggered. So from this I can obviously derive that level is 3. I set the flow to a positive value. I need to prove the invariant. And now I need to show that this stays safe until the next controller, until this method that I called here triggers. And it triggers if the level is above 10. So I have to stay safe while I'm below 10. And for up it's the same thing, except that I inverted. Nice, right? So now we can verify at least simple water tanks. But we need to verify the other water tank, because here we only look at very local information. I look at the method and I look what the method is guaranteeing to itself, what it's guaranteeing about the post region. But if I have these control loops, they are not local in this sense, right? Because I have several of them and they're running in parallel. So let's make more precise what I mean by a controller. Controller, for us, is a method which starts with a condition synchronization, has some statement and calls itself recursively. 2 more conditions, it's called from the constructor, so it's always active. And this statement contains no communication. So no wait, no get, no calls, only simple imperative statements. What does this mean? This means that whenever the object is idle, I need to check this condition and can schedule this method or not, or a process of this method. Which means that this guard here describes the post region in every possible situation. So indeed, if we have controllers, then the proof obligation looks very similar, except that I not only look at the called method, I also look at the set of controllers, and the post region is described as the negation of all triggers of the called method and the controllers. And again, the same thing for the constructor. Let's have an example, and let's again talk about modularity. So modularity is even worse, because when I change a controller, I now need to re-verify everything, because now I have changed every post region. But we gain more precision. I can now verify the original example. So this is the example from above, where I have shortened the flow condition here. Now what's the proof obligation for low? I assume the invariant. I can assume that I'm triggered. I have the translation of the method body, which is just that I set flow to 0.5. I prove that the invariant holds directly after executing the method. And now I show that while following the dynamics and neither triggering myself, which I call here, and not triggering the controller of up, which is defined here, I stay safe. Note that If I only look at low, I do not know whether up is active or not, right? So I need to put an additional analysis on top, which looks for certain patterns, and if I detect a pattern controller, I can use it in deductive verification. So we are going into a richer language compared, for example, with hybrid automata, but by using the additional structure, we can also easier detect patterns, which helps us with deductive verification. Okay, I want to quickly go over a few other details that you can find in full explanation in the paper before we come to the conclusion. So first of all, we can easily add method contracts. The method contract is a precondition on the pass parameters and a postcondition on the fields. And we can use method contracts to verify the communication with non-hybrid parts of the system. So we can use, for example, a verified cloud system in normal ABS and IoT devices verified with hybrid ABS, and verify the overall system using this method contract. You need to change two small things. You need to translate method calls now as a check, where you check whether the precondition holds of the called method, and if it does not hold, you set a certain flag, and otherwise you do not set anything. Now, the proof obligation is a bit more complicated. You assume your own precondition, you assume that the flag is not set, you assume the invariant. This method translation does not change except for this detail. Then you prove invariant, postcondition, and that you have not triggered any of these flags. And this part here does not change at all. You can deploy almost the same pattern for await, except that the condition is a bit more complicated. You check that the invariant holds at the moment where you suspend, and that it will stay safe in the post region, where this post region is now computed for this await here. So what are the methods which are guaranteed to be called at this point, and what are the controllers, right? And again, you set a flag otherwise. You need to do one more thing, because in the suspension something may run. You set all your fields to random values, and you assume only that the invariant holds and that the guard holds. And for gets, you do the very same thing with two small changes. The guard is always true, because you do not have a reactivation, and you always use true as the post region, because you don't know how long you will suspend, and because the way get works, no other object may run. So if you deadlock, you have to stay forever, because the complete object is blocked and nothing can run anymore. I have not talked about timed guards, so there are duration expressions and statements in hybrid ABS, but from a post-region perspective, they're very simple, because they just limit the time axis of the post-region. And I have also not talked about Xeno behavior, so you can detect simple Xeno behavior. So you cannot detect all Xeno behavior, but certain patterns. For example, you can detect whether your controllers are causing Xeno behavior or not. And what you do is, you look at the post region defined by the controllers, and you prove for every method that there is a lower bound, a constant lower bound, until you reach the event boundary, which means that there is always a lower bound between two discrete steps of controllers. So, to conclude this presentation, we have introduced a hybrid programming language, which is based on active object modeling, and we have introduced a deductive verification system for it, which is based on object invariant method contracts. And at the core, we have generalized pre-post condition reasoning to hybrid systems, where instead of only having a post condition which holds after the method terminates, we have introduced a post region where the invariant has to hold until the next method is guaranteed to be scheduled. By using method contracts, we are interoperable with the non-hybrid parts of the language, and what I have presented here has been implemented for hybrid ABS, which translates an annotated specified hybrid ABS class into a set of Chimera X proof obligations. For future work, we are looking for static analysis for more precise post regions. For example, if I can show that I'm not part of any deadlock, then I can actually use more precise post region if I translate a get. And also, we have used a lot that active objects are very strongly encapsulated. But you are not always in this situation. Sometimes they are too strongly encapsulated. Right? So how can we now use the ideas that I have presented in the last minutes in the systems where we have less guarantees on how objects interact with each other? And that's it. Thank you a lot for your attention.